Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about packing efficiency. So let's dive right into it. Now you have to understand this one core aspect of volume, meaning many times kilogram is something that we focus on. It's like how many watt hour it can carry in 1 kilogram. Okay, that's awesome. But here's the what is about the liter. Now you're like, why is that important? Here's the deal. 1 liter of diesel is powerful. 1 kilogram of diesel is also powerful. 1 kilogram of hydrogen will bitch slap diesel. But here's the deal. 1 liter of hydrogen at normal ambient point, basically something that you can carry on your hand without any issue, would be equivalent to nothing. Just a loud pop swing if it goes boom. Nothing. That's how little it is. Meaning you have to compress hydrogen to ludicrous level, meaning your tank would be idiotically expensive. And then also it will be very little. And you may be like, what if I liquefy it? Then also it will be very little, simply because to achieve 1 kilogram you may need as high as 11 liters just to achieve 1 kilogram. That's why volume matters. That's why we don't use hydrogen everywhere. It's just too goddamn dilute basically. So volume matter. It affects everything everywhere. It is one of those things that we have to thoroughly think about, because again, as I get more into this presentation, you will understand why the heck you can have lithium ions capacities here, like real world capacities here. Here's your car battery. It's like, why that, what happened here? That's the packing efficiency. That's what we are talking about here. So size is the core limitation in this world at this point in time, meaning if you can't carry it, if you can't contain it, if you can't distribute it effectively, it's not going to be used. Example, hydrogen. So it is one of those things that affects every day. Basically liquid containers that we utilize for rail transport, box container that we utilize for coal transport, all of these things are backbone of our industry, be it your milk cart, be it your water bottle, be it everything else. It is one of the critical aspect of our this world. And there are few core shapes that we utilize. Again, there are many shapes, but there are three generally core categories. We'll talk more about them. And the idea is all of these shapes will have some benefits and some consequences. And if you mess that part up, meaning if you did not select right application or right tool for the right job, it could ruin you. Example, Volt EV. We'll talk more about it. So let's start with the basic shape, the granddaddy shape, the cuboid shape, basically rectangles. Basically cube if it became rectangle. So cuboid is very great for modularity, meaning if you want to ship YOLO amounts of stuff, this is your guy. If you want to have, like, let's say a small car, let's say a BMW, certain variant of that, that's a small car, but you want to pack as much watt hour as possible in liter, because again, space is limited, you want cuboid shapes. So these are amazing. It has 100% packing efficiency, meaning if you pack 5-6 of these next to each other, there will not be a single void left, meaning 100% packing efficiency. Awesome. Meaning if you have one cardboard box and if you have a lot of small cardboard box, you can pack it up to like brim. So that's amazing. No gaps in between. That's awesome. Now you're like, okay, if this is awesome, it works. We do utilize it everywhere, like be it battery cells, be it basically giant container ship, which is the backbone of our entire global trade. What's the problem here? Why don't we use this shape everywhere? Well, this puppy has 90 degrees, meaning it's not good for pressure. So if you have a scenario, and if you are familiar with lithium ion, you must be familiar with yellow looking cells, which are generally lithium iron phosphate systems. They require clamping the hell out of them just so they do not swell up, because this shape is inherently weaker. So if I give you the same strength of the material, and if you put them into, cast them into basically a cuboid shape, it won't be strong because of the 90 degree. It will crack. And here's the problem with that. It's not kind of very uniform. It's not like, you know for a fact that if it cracks, only this part will crack. No, it could be like lol. So that is one of the issues. So if you are transporting solids, this is your guy. Like if you are transporting wheat, rice, coal, anything like that is like, contained inside a box, like TVs, your basically PlayStation, Xbox, those things, this puppy loves them. And here's the basically PlayStation engineers, especially in PlayStation 4, they worked extra hard to make sure the box is as slim as possible. Now you're like, why is that matters? Here's the each container ship costs some money, X amount of money. Now that X is fixed for Microsoft and for Sony. Both of them have to pay X. Okay, that's awesome. But here's the if Xbox can put 500 of them and Sony can put 1000 inside one box, it reduces the cost. Now again, they can make their console cheaper, or they can be like, hey, we can take the extra profit. So it does matter. Packing efficiency directly transfers to your profitability. So be very mindful of that. So what we learn? Cuboid, awesome packing efficiency. Not good for pressure management. Every time you are dealing with pressures, do not use this. Every time you want to deal with like absolute solid robust modularity, this is your guy. So that's shape number one. Then we come to the granddaddy shape, the spheres, the ball hardens. Now this is mathematically the most perfect shape. Now, like, why the heck that is? It has highest surface area to volume ratio, meaning how much metal you have to use just to cover a volume. This is like basically if you give 10 tons of metal, this will cover the largest amount of liters possible. There is nothing, no mathematical shape that even comes close to this. Cylinder is the next best thing, and which is not even close to this. Now you may like, does that matter? Well, here's the deal. What if your metal is expensive? What if the metal you are utilizing is used for liquid hydrogen, liquid helium, liquid nitrogen, basically things that are may need to be in pressure and may require metals that are cryogenically stable, which are ludicrously expensive. In those sort of time, it's like, hey, this tank design will consume 30% less steel. You'll be like, shut up and take my money. And not to mention, if you have surface area to volume ratio, that also means it's inherently the best insulator out there. Meaning, if you do nothing, if you just have this sphere versus every other shape, and you had zero insulation in all of them, for achieving the same amount of liters, basically let's say 10,000 liter in this, and cuboid will basically have much higher heat losses, because again surface area is huge on cuboid. This has the least amount of surface area, so meaning inherently it is acting as an insulator. So it's one of the best shape, and that's why sun is sphere. That is why gravity sooner or later always ends up collapsing everything into a sphere. That's the most stable shape. So this is amazing, and the capacity has like very non-linear response to it, meaning if you increase the radius just a little bit, the volume inside will go YOLO, meaning your surface area is increasing by, let's say, square, the volume inside is going up by cube. It's basically like a little bit equals lot of space. So this is one of the most amazing thing. And if you ever have to deal with high pressure, meaning basically putting liquid under very high pressure, this is your guy. If you want to put a very cryogenic liquid which requires very expensive insulation, this is your guy. You want to be stable in very high stressful situation like sea crossing, this is your guy. So spheres are awesome, but they have worst packing efficiency, meaning if you have to carry multiple of them, you can see how much space is there. Again, these spheres are not just on top, it's also on the bottom. So get that point, like there's so much space wasted. Like if you have so many balls there, like you can notice, like you can have a person walking around there. So it have very poor packing efficiency. So meaning if you have a larger box where you are putting this puppy in, they will have way too much empty space. So spheres have their use cases. Again, they are being used in real life, they are being made in real life, they have their certain advantages, but if you really want to do something interesting with it, it does come with some consequences. It's really bad at packing efficiency. So these are the two base shapes. Then we comes to the complex shape of cylinders. Now cylinder is a kind of good compromise between sphere and cuboid. Cuboid has very good packing efficiency. Cylinders, not that good, but good enough, meaning you can make your cells out of it. And it is good at pressure, not as amazing as basically a sphere, but good. Compared to a cuboid, it's good, meaning that's why you will rarely hear people talking about like, oh, you are using this 18650, you have to clamp this puppy down. No, simply because the cylinder inherently can be designed in such a way that it's like, dude, I don't expand. It's like, I got this. And because cylinder is kind of a predictable shape, they have a basically vent fuse on top. Basically it's gonna vent gases if it ever reaches a point of swelling, so to say. So inherently it's very good at pressure, and it does have good packing efficiency. Not as good as cuboids, but good enough where it's like from a distance, if you blur your eye, it's like more or less close enough. It's like almost 70% of space filling, so it's good. And it does have like basically the larger you make it, the surface area to volume ratio improves. Now, and not as amazing as sphere, but you can notice that like 18650, Tesla's first foray into electric cars, they were surprisingly smart about this. Because here's the deal, every company before Tesla was also trying to make lithium ion cars. It's just like they tried to make it, but they forgot the one thing: can you goddamn mass produce it? Elon Musk was like, dude, I'm making an EV car. Even at best day, I'm not gonna sell 100,000s of those. I'm barely gonna sell few thousand. Like I'm talking very early as in like when they were buying chassis from Lotus car company. So in that days, they were like, hey, what if we buy something that is off the shelf? 18650 were used in drill packs, laptops, power banks. So it was like mass produced like hell. So they went to Panasonic. It's like, hey, Panasonic is like, okay, that's just like 30% increase in our production capacity. That barely noticed anything. Every other company that tried to make basically I talked about Volt, they made amazing cell packs, which was really good at packing efficiency, really good at thermal capacity. Everything was awesome except the cost. They went bankrupt because of the cost. And they are like, here's the Tesla was like, you know what, let's be real, let's just buy what we can actually buy, afford what we can actually afford, and make a company. They got there. Again, this was good but not great enough. Then they went to 2170, even bigger. It's only 20% bigger, but it does have significant advantage. Like jumping from this to this is good. And then they realized like this was a intermediate step where they're like, I'm barely doing anything improvement. Then they went into 4680. Now if this puppy ever reaches mass production, actual market, actual car, to the public, it is still expected to take 2 more years from this point onwards. Is going to change the game, meaning any company that is using this puppy will be like, I got this. Every company that is not using this, please go out of business. That's how bad it will be. Like, to give you a context, that's like almost every other car company is using this AAA battery. Tesla will be using AA. Now it's like, again, that's not that big, but here's the funny thing. If this is 1x, this is 2.5x. One of this is better than 2 of this. That's why. And again, there is consequence of that. Like Tesla does not always use 2170, especially in their high-end models, because it does have the consequence. It does not dissipate heat faster. But again, too much volume, very little surface area. That's very bad if you want to cool this puppy. So they generally go back to 18650. I think somebody had like freaking misplaced this image. God damn it, that happens. So how the heck they're gonna handle 4650? Again, this is why they're tabless design. That's why without tabless, if you make this, it will have very low basically amp capacity. Basically surge charges, it will not be able to handle that much. But because it's tabless, it's far more conductive. So inherently it can compensate for poor surface area by improving conduction, basically thermal conduction. Both sides will be much better thermally conductive, so it can wick heat away much more efficiently. So that's the whole point. That's why we use aluminum beverage can in cylinder. Like this puppy is under pressure. It's like very thin. It's like paper thin aluminum, yet it can handle good amounts of pressure. That's the reason behind this. It's like a very good pressure handling capacity of a sphere and packing efficiency of a cuboid. Most commonly used for everything. So we have to talk about one of the core aspect of engineering, which is balance. There is no one scenario where it's like, this takes care of all. That does not happen. Physics does not allow that. That's like universal law. That shall not happen. So one thing you always have to balance is cost and efficiency, because you may be like, okay, lithium ion is only this much. We cannot get too much range. Here's the deal. If anybody tomorrow makes a car that even achieves 95% of what lithium ion can actually do in real world, you'll be like, dude, how the heck your car has that much range? Like, wait a minute. What I'm talking about, here's the deal. This is lithium ion pack, real world, in use, in mass production. Awesome. 102 kilowatt hour capacity. That's some serious amount of oomph there. Now this is around 461 kilogram. Now everybody focuses on that, like, it's like 100 kilowatt for this much. That's good. But here's the deal. If you talk about like what is the peak specific energy, pack specific energy, as in, sorry about that, 160 watt hour per kilogram. Now, if you have ever looked into Wikipedia page of lithium, and that number is way too small. Why the heck that number is too small? Simply because of packing efficiency, its proportion of cell to pack mass is 63%. Meaning it has too much goddamn empty space. It's empty most of the time. That's why Tesla is trying to go from smaller cell to a little bit bigger cell to like huge cells. That's why packing efficiency matters. It's like, here's your cell pack, here's what lithium ion actually does. Like basically, if you only buy one lithium ion, like, this is my lithium ion, it has amazing capacity at this point in time. But here's the deal. How the heck you pack this in like, hundreds of these into such a place where it's like, not even a single square millimeter is wasted. Yeah, that's the issue. That's why you have to understand. You have to balance this out. Like, that's why when Volt was trying to make such a hybrid car, they achieved like such a small battery, they still achieved like very good range on that, like for such a small thing. It's like, how they achieved that? Because they were using basically cuboid shape, basically. And cuboid shape, they had all of the amazing features, but it was too goddamn expensive to manufacture. So that's why they kind of failed, bankrupted that division of the system. So you have to understand. And that's why like BMW are trying to make Samsung manufacture cuboid shapes. Awesome, super amazing. Packing efficiency, really good. Meaning small car, very good packing. Like they can exceed this 63% without even like, batting an eye. Consequence, it's BMW and it's idiotically expensive because the cell itself is expensive. So it's one of those things. And again, I have noticed this supercapacitor company, they are making hexagon. I was like, they really want to improve the packing efficiency, because this actually beats cuboid also, because cuboid cannot grow further. Like you have to give it a square space. But what if you have uneven space? Hexagon is the best. That's why we generally, whenever you're making a telescope, you are using small hexagons like a James Webb telescope. It gives you almost perfect circular coverage if you have a circular space. Meaning if you have inorganic outline, this is the best way to fill it up. That's why honeys, you generally utilize hexagon shapes. So they are using this, like assume you do not have to worry about cooling, and this does not have any chance of swelling. Again, it will have good enough characteristics compared to cuboid. It will still manage its shape, but it won't be as strong as a cylinder. So it's a like again, there is a compromise, but it will have amazing packing efficiency. Meaning, if you are making a bicycle and let's say for some reason you found us to use super capacitors, you can pack this puppy properly without even a single hair of space in between them. Meaning your proportion of cells to pack mass would be much higher. You can achieve like 89% or even 95%. At that point in time, you will be surprised like how far our electric cars can go if we can just sort this puppy out. I'm not talking about chemistry. Chemistry is good. Like, we got the chemistry. We're good. It's just how the heck do you go from packing efficiency of 63% to 95%. That's the end game. Again, physics is not stopping it. That's why you have noticed companies are trying to make blade cell packs simply because blades are much easier to pack together. So it's one of those things that we do not think about, but it matters a lot, and that defines whether you succeed or fail, or how far your career. Imagine it is if this 63% became 40% better, this will add 40% more to it. It's like same size, add 40% or even 30% more. People will whoa, this car has ludicrous range. We just have to improve the packing efficiency, and again, conduction also, because again, cooling would become an issue if you do that. So again, always a trade-off. Always you gotta balance this puppy out. So this was my presentation on packing efficiency. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.